So hello everyone, welcome back to another particular lecture series of our Reagent Chemistry course, and this is the class 10, and here we are actually discussing about the homogeneous hydrogenation. So previously in our previous lecture, this is the class 9, we are talking about the Birch reduction in details. So now we are talking about the hydrogenation by using metal catalysis. Okay, so first let us understand the hydrogenation. Basically you all know about the hydrogenation. Hydrogenation is nothing but a hydrogen addition to an unsaturated compound to make this saturated. Okay, now here hydrogenation can be done by various process, but here we are actually focused on the metal catalysis pathway. Okay, so now hydrogenation we can simply classify in three different part. This is the homogeneous hydrogenation, heterogeneous hydrogenation, and asymmetric hydrogenation. Homogeneous hydrogenation suggests that the catalyst and your the compound having the same phase, whereas the heterogeneous hydrogenation means that the catalysis and your reactant are in the different phase. And asymmetric hydrogenation, that means the stereoselective hydrogenation that we are actually not discussing here. Asymmetric hydrogenation we will discuss in our asymmetric synthesis part. Okay, so we are mainly focused on this particular two. This is the homogeneous hydrogenation and heterogeneous hydrogenation. So homogeneous hydrogenation is a single phase reaction and the heavy metal based catalysis has been used. Whereas in heterogeneous hydrogenation, it is a two-phase reaction and basically palladium or nickel based hydrogenation takes place. And this particular reaction, that is the hydrogenation as a double bond, is thermodynamically favorable. And that's why actually this reaction is felicitated. Now let us talk about the homogeneous hydrogenation in details. But before that, we have to know that ease of reduction of functional group to a catalytic hydrogenation. Okay, like if you see this particular group, that you can find here that by using catalytic hydrogenation, that means the metal catalysis, by applying metal catalysis, benzene to cyclohexane is the hardest reduction to do because here actually we are losing the aromaticity, so it is the hardest to do. Now as we go up to this particular arrow and the functional group comes here, this is the easiest to do hydrogenation by using catalysis, metal catalysis. Like the most easiest job to do hydrogenation by using metal catalysis is acid chloride to aldehyde, then NO2 to NH2, then here is the RC triple bond C. This is the triple bond, or you can say the alkyne to alkene transformation, then aldehyde to alcohol, then double bond to single bond, and then ketone to their corresponding alcohol. So you can find here that the most difficult task to do is benzene to cyclohexane, and the most easiest task to do by catalytic hydrogenation, that is the acid chloride to aldehyde. Okay, so now let us talk about the homogeneous hydrogenation, and here we are mainly focused on the Wilkinson catalysis. Okay, so Wilkinson catalysis is a homogeneous hydrogenation, and it is nothing but this, that rhodium triphenyl phosphine whole 3 chlorine. Okay, so this is the our catalysis, and this is the organometallic compound, and it is show the syn hydrogenation. Okay, this is the stereoselectivity, like syn hydrogenation takes place. Less substituted double bond has been reduced first. Isolated double bond reduction more than conjugated one. This thing we had actually discussed in when we are doing actually question answers. Now the most important thing is what should be the mechanism of this particular Wilkinson catalysis. So the mechanism is the traditional organometallic compound have their own cyclic mechanism, where three major step has been observed. First one is the oxidative addition. Oxidative addition is basically nothing but that the reactant are actually add to the metal catalysis, then hydrate transfer, and then reductive elimination. Reductive elimination means the product has been removed from the catalysis. So we'll discuss in brief or in elaborate way in the mechanism. But before that, we have actually see this particular reaction. Now here you can see that here two type of double bond is there. One is the exocyclic double bond, or we can say that isolated double bond, and this is the substituted double bond. Now in presence of Wilkinson catalysis, what happened that the selectively that isolated double bond has been reduced. However, this particular double bond is not reduced. Okay, so you have to remember this small thing. Now we are talking about the mechanistic pathway. So the mechanism is the initially this is our the catalysis, rhodium triphenyl phosphine whole 3 and chlorine is there, and if you calculate the electron number, it is a 16 electron species. That means it has a vacant site. Okay, now this particular hydrogen actually attach with this particular thing via oxidative addition, because here the rhodium is +1 state. After addition of hydrogen, rhodium is now +3 state. That means the oxidation takes place, and this is called the oxidative addition. Okay. Now what happened that one of the PPH3 ligand actually goes out of the catalysis, so that here is actually generate a vacant site, and now this vacant site is required to acquire the double bond, or we can say the alkene. So it will coordinate first, and after that uh, hydrate transfer takes place. You can find here that one of the hydrate are actually transferred here, and it generate this type of intermediate. Okay, and now you can find here that here is also a vacant site has been generated. Now the PPH3 is initially that removed, that again come back here to fulfill the vacant site. Now what happened that now a reductive elimination takes place. Now reductive elimination has been observed between this particular group and the remaining hydrogen here. So these two will combine and do a reductive elimination, and we got our product, and we got our catalyst back. And since we get our catalyst back, now this particular catalyst we again undergo the same catalytic path cycle to generate the particular alkene, or we can say the hydrogenation product. So this is the Wilkinson catalysis mechanism. We'll more elaborately discuss when we are discussing the organometallics compound, or we can say that the metal palladium mediated cross coupling reaction. Then we will discuss this in a further way. Okay. Now, rate of hydrogenation. So, as I already discussed, that Wilkinson catalysis have shown more hydrogenation over the isolated double bond, and because of the steric reason. Like here, you can find that this actually coordinate, and the PPH3 ligand and chlorine ligand are bulky enough also. So, what happened that the coordination takes place where the alkene have the lesser substituent, or we can say the isolated, so to eliminate the sterics. And that's why basically this particular styrene having the more reactivity towards the Wilkinson catalyst, whereas this particular tetra-substituted double bonds are not that much feasible. And also you can find here the cis product are more reactive over the trans product. So this thing you have to remember. And also there is certain facts is there on Wilkinson catalysis that you have to remember, that the first one is the less substituted and sterically less hindered double bond are selectively hydrogenated because of the steric issues. Also the exocyclic double bond are selectively hydrogenated over endocyclic double bond, that I already also discussed. Isolated double bond are more rapidly hydrogenate over the conjugate dienes, and terminal alkynes such as are hydrogenate more rapidly than terminal alkenes. That means the triple bond have the more affinity to reduction or hydrogenated over alkenes, that is a double bond. And interesting thing is other functional groups such as the CO, CN, NO2, aryl, esters are unaffected in this particular reaction. So this shows the selectivity of this particular reaction, that all double bond getting reduced. Now we are talking about the stereochemistry, as I already discussed, that it will always show the cis addition. Because of the mechanistic pathway, we can see that it will always provide cis addition. Now where should be the hydrogenation can be attached in the above of the plane or below of the plane. This is also depend by the substituent directed group. Like here it is written that if any chelating or hydrogen bonding group present adjacent to the double bond, then hydrogenation stereochemistry is depend on the stereochemistry of the chelating or hydrogen bonding group. For example, here this is OH is there, this is a hydrogen bonding group, that is the capable of doing hydrogen bonding. So in presence of Wilkinson catalyst, irrespective of that here it might face some steric issues, however it will show the same retain the same stereochemistry upon hydrogenation, because the uh, driving force is to this particular group, that is the capable of hydrogen bonding, and that's why the stereochemistry is exclusively matches with that particular stereochemistry. However, if the same compound, if there is a no hydrogen bonded group is there, like here, then Wilkinson catalysis will follow wherever it will find less steric hindrance. So here you can find that the cis addition takes place, but here the stereochemistry is not exactly mimicked by the adjacent group. So this is a very important thing that you have to remember this thing. Okay. So with this, we have to end this particular class, and I believe that it will enough for your Wilkinson catalyst and their reactions. So in the next class, we are talking about the heterogeneous hydrogenation, such as the palladium carbon mediated hydrogenation, or also nickel based hydrogenation mechanisms. Okay, so with this, we have to end this particular class. So thank you for listening.